to a similar problem to the fire truck example that we did, but it's slightly different. It says a bat is flying at 25 meters per second and sends a 30 kilohertz chirp at a flying insect that it is chasing. So the bat is moving in the same direction as the insect here. So imagine this is the bat here, moving this way, right? And then we're given the speed of the bat 25 meters per second, and then the insect is also moving this way because the bat is chasing it, but we don't know the velocity of the insect, right? So then it says it's chasing and receives back waves of frequency 30.7 kilohertz. So it sends out this sound wave, very, very, very high frequency, and it's above the frequency that we can hear as humans. The highest frequency we can hear as humans is called ultrasonic frequency, and that's roughly about 20,000 hertz, 20 kilohertz. So anything higher than that is called an ultrasound, right? So then the waves reflect off the insect and come back, and then the bat hears a frequency of 30.7 kilohertz. What is the speed of the insect based on this information? And then we're going to assume that the temperature in the air is 20 Celsius, so that the velocity of sound in the air is 343 meters per second, right? So then what's going to happen here? Well, in this example, there's actually two Doppler effects that is happening. So assume first the wave is going like this, right? So first answer the question, when the waves reach the insect, what frequency will the insect receive? What's the perceived frequency of the sound waves from the perspective of the insect? So we have here f prime is equal to f, velocity of sound. Since the insect is the observer, right, and he's moving away from the source of sound, that will tend to decrease the perceived frequency, right? So we have velocity of the sound minus the velocity of the observer. And the velocity of the observer is actually the insect, right? And then, but the bat is moving towards the observer, so that will tend to increase the frequency, right? So f minus velocity of bat, right? So both of them are minus. So we have here f prime, we put here 30, right? 30 kilohertz. Right now I'm not going to put kilo, but we know the answer is going to be in kilohertz. Here we have 343, right? Minus velocity of the observer, but we don't know the velocity of the observer, the velocity of the insect, right? So we just put here v. The velocity of the observer is v, or we could put vo if we want. And then here we put 343 minus the velocity of the bat was 25, right? So we put here 25, and then we're going to get what? And so we have this ratio then, but we don't know what the answer is. So that's the perceived frequency of the sound wave as coming and reaching the insect, right? So then the insect takes this sound wave, and the sound wave gets reflected off the insect and now goes back to the bat. The bat now becomes the observer, the source becomes the insect, right? So this one, the waves are going this way, the insect is flying this way. So when the sound wave reaches the insect, the sound wave then bounces back, reflects off the insect, like this. And then here's the bat. So now the observer is the bat. And now the source is the insect, right? So over here then, it's more correct just to put velocity of insect for now, because the insect is changing roles, right? At first they're the observer, then they're the source. So let's just put here velocity of insect. And that's better now. So then what happens? So now, since the insect is moving away from the observer, he's the source, that will tend to decrease the frequency. But the bat becomes the observer, and the bat is moving towards the source, so that will tend to increase the frequency. So we have here f double prime is the perceived frequency of the sound waves as coming back to the bat, right? So there's two Doppler effects happening here. So then that's equal to f prime times velocity of the sound, 343. So now who's the observer, right? Always on the numerator you put the observer. So the observer is the bat. The bat is flying towards the sound waves this way. So that will tend to increase the frequency, right? So we put plus velocity of bat. Because the bat is the observer now, you put it in the numerator. Then divide it by 343. Now, should we put minus or plus? Well, the source, which is the insect, is moving away from the the observer, right? Moving away, that will tend to decrease the frequency. So in order to decrease the frequency in the denominator, you put a plus. So plus the velocity of the insect. And then what is this now? F prime. And then so on the top, we put 343 plus 25 over 343 plus V insect. Right, so then we simplify that, we say F prime, and then we add 25, 368 over 343 plus V insect. Right? So then what we're going to do, the F double prime, the problem already told us, because the F double prime is the perceived frequency of the sound waves when they came back to the bat, and the bat heard 30.7 kilohertz, right? 7, right? And that's equal to F prime. Now what was F prime? So let me just write it here, 368 over 343 plus V insect. Right, but the F prime, we had an expression for it here that I erased, right? The F prime was equal to 30 times 343 minus V insect over 318. Right? So we put down this whole thing, the 30.7, right? So we have 30.7. Then we can take the 30 to the other side, divide by 30, both sides. Then the 318 goes to the top, we have 318. And then the 368 goes to the bottom, 368. And then that's equal to 343 minus V insect over 343 plus V insect. Right? Plus V insect is equal to 343 minus V insect, and then distribute this in, so multiply it by 1.88. So the velocity of the insect comes out to be 21.06 meters per second. So right off the bat, no pun intended, right off the bat will realize that the insect is going slower than it, right? Because the bat was going 25 meters per second, and then the insect is going 21 meters per second. That means that he doesn't necessarily have to increase his speed, he can just keep 25 meters per second, and he will eventually catch up to the insect. And so, you know, depending on what their distance is, it's going to take them a certain amount of time to catch up. You see an example here of a double Doppler effect taking place, and where the sound wave is first going, reflecting off the observer, and now the observer is becoming the source, and then coming back to the original source, and the original source that's sending out the sound wave is becoming the observer, right? So it's a double Doppler effect. Okay? Thank you very much.